Yep, go for it.
Oh, so hi everybody. My name is Juliet, and this is my final presentation of my master's degree. My project is machine learning of F18 sodium fluoride PET-CT radiomic features for prediction of coronary calcification scores. And my supervisors are Martin and Jake. So I would like to begin with an acknowledgement to University of Western Australia, the Medical Physics Research Group, my supervisors, Martin and Jake. This is Jamie, the cardiology fellow that helped with the clinical trial and answering all of my questions. Nathaniel and the ML cluster, Pechman, the program chair, and Mubasha for all of your valuable comments. And most importantly, all the patients that participated in the clinical trial that made this whole research possible. So we have a lot of contents to go through, so I'll jump straight into my presentation. So I would like to begin talking about what is cardiovascular disease and what is coronary artery disease. The cardiovascular diseases are responsible for around 17.9 million fatalities annually around the world and contributing to 31% of the global mortalities according to WHO. And coronary artery disease is a category of cardiovascular disease and is responsible to 9 million of deaths annually, and it's one of the leading causes of mortality among all cardiovascular diseases. So what is coronary artery disease? It is characterized by the accumulation of atherosclerotic plaque within the coronary arteries. It restricts the blood flow and oxygen deliveries to the myocardium, which is the heart muscle. And such plaque buildup in the coronary arteries can lead to many symptoms, including chest pain, short of breath, heart failure, arrhythmia, and most seriously is heart attack. So the advancement of coronary artery disease frequently occurs without any apparent symptoms until the disease has substantially progressed. And such silent progression presents a significant challenge for early detection and risk stratification for coronary artery disease patients. In the 1990s, the Agatston score was invented to calculate and quantify coronary artery calcification. So it uses CT scans and sets a threshold of 130 HU and an area of 1 millimeter squared for each lesion. And how the calcium is quantified is by multiplying the area of each lesion by a factor that's determined by the peak HU within the region of interest. And the total coronary calcification scoring is the sum of each lesion within the coronary artery. And in such way, people were able to quantify the coronary calcification within the coronary arteries. So the first picture is a severe case of coronary calcification of end-stage patient. You can see heavy calcification within all of the coronary arteries. And the second picture is a CT from the 1990s. It's 4 non-consecutive CT slices of a 56-year-old man with coronary artery diseases. And we can see this calcification, the white specks in the left anterior descending artery, the diagonal artery, and the right coronary arteries. Here, I just want to see and show everybody how it looks like. So, although the coronary calcification score is a useful risk factor, but it has its limitations. Firstly, because it uses a threshold for each lesion, it can result in overlooking of small lesions of microcalcification. Secondly, there's no information in the calcium score that gives you information about the temporal dynamics of the lesion, meaning that we don't know if a lesion is active or stable, if it's progressing and developing further, or is it just stable. So we need something else. Sodium fluoride, F18 sodium fluoride, was originally used as a bone tracer, but in recent years, it has shown great excellence and safety in cardiac imaging. It will show increased signals of early-stage microcalcification that is often missed by CT scans. Also, their research also has highlighted the potential of F18 sodium fluoride as a reliable predictor of coronary calcification progression. And there's a research done here at St. Charles Gardner Hospital on the potential of F18 sodium fluoride as a predictor of coronary calcification progression. So in this research, our aim is to use F18 sodium fluoride to quantitatively predict the follow-up calcium score and to be used as an additional risk factor so that the clinicians have an idea of how each lesion will progress 2 to 3 years down in the road as an additional risk factor for better patient management. This image that's showing on the screen right now is showing how sodium fluoride can predict calcium progression. So the two rows are two patients, and the first column is the baseline CT scan, and we can see the two patients have similar level of calcification at their baseline CT. And the second column is the baseline PET. You can see one patient have a higher PET uptake at the lesion compared with the other patient. And the third column is the follow-up CT. And we can see the patient with higher PET uptake had much higher calcification progression in their coronary arteries compared with the one with less PET uptake. So instead of just looking at those pretty pictures, we can also quantitatively describe the images using mathematical methods. So the Image Biomarker Standardization Initiative standardized many radiomics features, which are quantitative high-throughput information from medical images. These include first-order, intensity-based features, shape and size, describing each region of interest. Also, there are higher order texture features, including GLCM, GLRLM, GLSZM, and GTDM, GLDM. Due to the limitation of this presentation, I won't really go into describing what each one of the categories of features, what are they describing, but all of the radiomics features are describing quantitative informations of region of interest of medical images. And to extract these radiomics features from medical images, different settings can be applied. Firstly, different image filtering can be applied with feature extraction. These image filters can either smooth, enhance, or sharpen images, and the image filters has the potential of enhancing certain features. And also for the texture feature extraction, everything other than first order and shape and size, grayscale discretization is something that's needed to discretize the grayscale levels of the entire image into different bins. And with these settings, it can be applied with our good friend Python. So there's a library that is established using the IBSI standards. So this library allows us to extract radiomics features from medical images with different settings. So the stability of these radiomics features is important because if we are going to use it clinically, we would want to know that they are reliable clinical indicators, that they will represent the same information every time. So there are two aspects to feature stability, including repeatability and reproducibility. So what is repeatability? It denotes the consistency of feature extraction when analyzing identical scans at multiple time points. So things that is related to repeatability of radiomics features, including organ motion, patient positioning, and physiological transformations. What is reproducibility? It captures the capability of achieving consistent radiomic results across different settings. And these settings include from different scanning apparatus, from different imaging protocols, or different segmentation methods. So what we want to make sure is a feature is stable and only affected by the pathology itself rather than by different imaging setups, so that we know this feature is reliable to be used clinically. With all of these, we talking about sodium fluoride scans, radiomics features. We like to combine it with machine learning and to do our prediction of calcium score, of the follow-up calcium score. So what is machine learning? It is a subset of artificial intelligence that focuses on development of algorithms to enable computers to learn without being explicitly programmed. So what exact does that mean? It's quite a multi definition. So a computer program is set to learn from experience E with respect to task T and some performance measure P. If its performance on T as measured by P improves with experience E. And a typical machine learning solution includes studying the problem that needs to be solved, getting all of the data, and train the ML model with the data, investigating the data, and produce a solution using the ML model. We inspect and evaluate the solution, implement it, and had to have a better understanding of the problem, and repeat the whole process again and again. So with all of these background knowledges and tools, we aim to achieve and investigate the following. The first thing is we would like to investigate the variability of radiomics feature values attributed to segmentation discrepancies using Wendman-Whitney U-test, CCC, concordance correlation, Pearson correlation, and intra-class correlation coefficient. We also would like to investigate the individual radiomics features association to follow-up calcium score using a univariate Spearman correlation coefficient. We are also going to use a multivariate machine learning models to construct a machine learning model to predict the follow-up calcium score using calcification algorithms, for example, like random forest, gradient boosting machines, support vector machines, and logistic regression. So let's talk about data collection now. The data for this research is from the VICOVAC trial, which is conducted here at St. Charles Gardner Hospital. All the patients from the VICOVAC trial have a baseline CT to calculate their baseline calcium score. They have a baseline PET image and another PET image around 3 months after the baseline. They also have a follow-up CT taken about 2 to 3 years down the road for calcium score calculation, 2 to 3 years down the road. So all the images are acquired using ECG-gated screening for CT, for calcium scores. For CSCT, calcium score CT, and F18 sodium fluoride PET images were taken, followed by a 30-minute rest after a 250 megabecquerel injection. Controlled heart rate was followed during the PET imaging. With segmentation, so the PET and the CT images were co-registered to the same resolution and manually segmented by the clinicians. Image pre-processing, so all of the image and the segmentation, the masks of region of interest were converted to NIfTY format, and the PET images were converted to SUV values for standardization. For the NIfTY format is so that it can be processed much easier later on. For feature extraction, so 117 distinct radiomics features standardized by IBSI from each region of interest were extracted, and there were various beam width and image filtering were applied with the feature extraction. How does our data look like? So the VICOVAC trial have 141 patients, and all of them have a manually segmented contour by the cardiology fellow. Within the 141 patient, 90 have a valid follow-up calcium score around 2 to 3 years down the road. Also, within the 141 patients, 28 patients have an AI segmented contour, which is trained on the manual contour, and 28 patients have an additional AI segmented contour using an NUNet. And 17 patients have both AI contour and follow-up calcium score. So the 28 patients with both manual and AI segmented contours will be using them to to evaluate our feature stability, since we have two sets of different contours from different sources. And the PET level discretization, we've used 0.5 to 0.2 SCV, increment 0.05, and the image filtering that was used includes Laplacian of Gaussian with different sigma values, square, square root, logarithm, exponential, and 8 different wavelet filters. The feature's stability was evaluated using both baseline CT baseline PET and the follow-up PET. There are 4 regions of interest for 4 different coronary arteries. We also have 90 patients that with the valid follow-up calcium score that we're going to be using them for the univariate and the multivariate analysis. These are some of the patient information. Due to the time limitation, I'm not going to read them, but these are the percentage of gender, age, and etc. for general patient information. With feature extraction, for each one of the patient, we extracted features, just a summary of what was mentioned before, for 3 of the modalities, for the 3 of the image sessions, for 4 of the arteries, for region of interest. For 4, we have 4 different grayscale discretizations that was applied, and 17 different image filtering that was applied with the feature extraction. And for all of these settings, for each one of these settings, 107 radiomic features were extracted. For each one of the patient, we have 87,000 radiomic features that was assessed. So now let's go into the first aim, feature stability. We evaluated the feature stability using 4 different statistical tests. Mann-Whitney U-test is a non-parametric test without assuming data normality. And if the p-value of the U-test is less than 0.05, null hypothesis is rejected. It means that the 2 sets of samples have a statistically significant differences, that the 2 sets of radiomics features are not stable. That's what we consider the results from Mann-Whitney U-test. For the concordance correlation, it quantifies degree of agreement considering both precision and accuracy. So we consider a feature is stable if it's greater than 0.95. For Pearson correlation, it's used to assess the linear relationship. The absolute value, the greater the value means the higher they are more correlated. So we're using the threshold of 0.6. If the absolute value of the correlation coefficient is greater than 0.6, then we consider the feature is stable. And for interclass correlation, ICC2 is used to assess the consistency of 2 sets of samples across different conditions and tools. And the threshold of 0.75, using numbers from literature, were used. So a feature have ICC above 0.75 is considered stable. So before we show the visualizations, we're going to show what are the key points and key findings from the feature stability results. Firstly, the Mann-Whitney U-test, Pearson, CCC, ICC, all of these statistical test results align quite well with each other, especially the Pearson correlation and the ICC results were almost identical. So the beamwidth settings had a very minimal impact on feature stability. A smaller beamwidth yielded a slightly better fractions of features with good stability compared with the larger beamwidth. Image filtering. So image filtering has affected the feature stability a lot more than beamwidth, and specifically the simpler filters, logarithm, square root, wavelet LLL filters, have progressively improved the proportions of stable features. The coronary arteries, we do find that 2 of the coronary arteries have a lot more stable feature than the other 2 coronary arteries. So left anterior descending right coronary arteries have a lot more stable features than circumflex and left main artery. And the first order and GLCN features have shown highest stability across different feature categories. And they were also the least impacted by image filtering settings. So on the contrary, shape features showed the least stability. Some of the visualizations of the key points that we just mentioned. So the first graph is a heat map showing the portions of features with good stability for different beam width settings and different image filtering settings. So the more blue means there are higher percentage of higher percentage of features with good stability, and the more red means for the combinations of beam width and image filtering, the features are less stable. And as we can see, the variations of color horizontally is much less than the variation of color vertically. That's one of our findings, that the beam width has impacted the feature stability a lot less than the image filtering settings. And our original image is right here, and we can see the filters that performed better than our original image, logarithm square root waiver LLL exponential. In addition to that, as expected, our high-pass filters with the HHH3 high-pass filters gave the worst stability. It's kind of expected as it's sharpening the details of the images, and our low-pass filters with the LLL triple low-pass filters is giving one of the better feature stability as it's kind of smoothing everything. And there's something to mention here in advance is that there's a trade-off between feature predictability and stability. Is what a filter, for example, with LLL, could have make a feature very extremely stable, but it could also remove the information from the feature to make it less to have a less predictability, which is not something that we want. The second graph here is showing individual feature category, first order, GLCM, etc., and the percentage of features within each different feature categories that are stable. And we can see first order and GLCM features are the most blue, which means they have the higher percentage of stable features. It's not very easy to see here, but LAD and RCA or different image modalities have consistently given higher percentage of stable features than the other two coronary arteries. So this is another heat map that we're showing different feature categories against different image filters. And we can confirm the previous finding that first order and GLCM features gave the highest stable features. But we can also see the variation of color vertically with different image filtering settings for first order and GLCM features, a lot less compared with the rest of the feature categories, which means they're more invaried to image filtering settings than the other features. So we have to keep the results of our feature stability at a very high level due to the time limit. So, but if anybody's interested in what exact features are more stable and less stable, they're all in my thesis, if anybody's interested. So discussion of feature stability. So this person, not trying to pronounce his name, has and Ha both advocated for absolute quantization of PET radiomics, just due to the different ranges of PET grayscale levels across different patients, and it's better to standardize the grayscale discretization with fixed beam width method. And this study has found that, and for Ha, he's found that the final beam count between 16 and 128 is optimal for PET grayscale discretization, and this study found that 0.5 and 0.1 SUV gave the best stability, which is corresponding to the final beam count of 16 and 128. Reproducibility. So we couldn't find a reproducibility for F18 sodium fluoride, but we found a study of reproducibility for MRI features from the myocardium. And the study by Jiang found 32 to 47 intra and intra observer reproducibility, and this study has found a similar number for feature stability for the reproducibility of the radiomics. It was also found by this person that if a feature is stable in test-retest studies, it's most likely to be stable against reproducibility studies. It gave us confidence to compare our results with the test-retest studies as well. So Nathaniel, master's thesis, has concluded there are certain Laplacian of Gaussian and wavelet filters that improve feature stability. And what we found is actually very different from what he found. Is we found the simpler filters, logarithm, square root, and wavelet LLL filters improve feature stability. It's quite different, but with similar findings were that bandwidth was found to have minimal impact on feature stability. A systematic review by Traversal, he concluded that by most radiomic study, first order features have the greater reproducibility compared with shape and texture features. This is consistent with our findings. But this other person has highlighted that radiomic studies is more case study specific. Sorry. We do have similar findings, even on a high level. We do find some similarity of our findings between other studies' findings, but into the details, each radiomic studies have very different findings. So there are standardization by IBSI and RQS, but there are still a lot of different influencing factors into radiomics studies, and a larger cohort and multi-center research is needed to validate the findings from this research. We're going into the univariate analysis of Spearman analysis. So objective is to assess the individual features association to the follow-up calcium score using Spearman coefficient. And we're going to use both baseline CT and PET radiomics features from the manual contour. So Spearman correlation coefficient evaluates both linear and non-linear associations, other than the Pearson correlation, which only assesses the linear association. We are going to assess such association at the artery level without differentiating which segment of the artery it is. So for the Spearman analysis, a coefficient will yield to indicate how strong the relationship is. Also, there will be a p-value indicating how the significance of the association, like how much the confidence of the association. If the p-value is smaller than 0.05, then we deem the association as meaningful. I'm going to quickly go through the univariate analysis result. So in general, the CT features had a much stronger correlation with the follow-up calcium score than the PET features. But note that the calcium score is calculated from the baseline CT scans, so it is giving the CT scans an advantage. No PET features showed strong or moderate correlation with the follow-up calcium score. So although the previous square root, logarithm, exponential filters gave good feature stability, they didn't give a good feature predictability. So with the application of those filters, the amount of the features are actually less associated with the follow-up calcium score. So as we mentioned before, there is such a trade-off. So this heat map on the left is showing amount of features, taking a cutoff of 0.5 for PET features that are associated with the follow-up calcium score. And the heat map on the right is showing amount of features from CTs that's correlated to the follow-up calcium score. And we can see the wavelet LLL filter and the original image gave the higher percentage of features with good predictability. And for CTs, it's two other wavelet filters. And we can also see, similar as our stability study, the bandwidth change did not change the feature predictability by too much compared with the application of image filtering. So there was a study using the same cohort, but only using tissue background ratio that showed the radiomics from sodium fluoride is good for predicting calcium progression. But here, this study we will explore the full potentials of all radiomics features. This is a finding I mentioned before, the filters that enhances the amount of predictive features. As mentioned as was shown in the graph, CT features strongly correlated with the follow-up calcium score comparing with PET features. There's a study that we cannot find exact sodium fluoride PET studies, but we found a study using SPECT to correlate with the calcium score, and it was found by this person that there's not a single SPECT radiomics to have direct correlation with the calcium score, which is quite a bit similar with our finding that there's not a PET feature that has strong or moderate correlation with follow-up calcium score. So again, we apply Spearman correlation without differentiating arteries, and this will be later validated by the feature importance analysis with machine learning that the segment of the artery is one of the low importance features in stability. Low important features for follow-up calcium score. Yeah. Again, we need more standardization and larger cohort in both, better standardization for both these type of studies, also standardization of understanding of calcium score to validate the results of these. Okay, so we're going to jump into the multivariate ML method. I'm trying to go a bit faster. So use the previous results, stability and predictability analysis. We're only going to use the original image and a bin width 0.1 for PET images. And the follow-up PET features were not used due to they won't be available in clinically later on. Only features from manual segmentation was used for training of the ML model. So the 19 patients have both baseline follow-up calcium score. They are partitioned into 80 and 20 split. 72 in training, 18 patients in testing, and we make sure the 17 patients with AI segmented contour were all in the testing so that we can evaluate model on both manual and AI segmentations. Refinement, so we will restructure the whole data set at artery level so that we have more instances in both training and testing set. And the feature and model selection was conducted on the training set. Due to the broad range of calcification scoring and the limitation of the size of data set, we'll be using classification models. And the follow-up calcium score is partitioned into 3 groups, 0 to 25, 25 to 100, and greater than 100. So we will be training 3 models, clinical, radiomics, and a combined approach to compare the capability of radiomics features versus clinical indicators. We'll be using 5 classification models, random forest, SVM, logistic regression, and 2 gradient boosting method. We'll be first performing a pairwise correlation to eliminate features that's greater than 0.8 correlated with each other. And we'll be using a data pipeline to scale the numeric features and to encode the texture features. The text features. We use recursive feature elimination with each one of the 5 models to pick 5 top features with each one of the 5 models. And we mix and match of the 5 feature set with the 5 models. And the combination that yields the highest cross-validation FI macro score was identified. And then we do a hyperparameter grid search on the best model to using 5-fold cross-validation and F1 score. And the fine-tuned hyperparameters will be with the model will be our final model for that category. So recursive feature elimination results. So for the clinical model, we used all of the clinical features, include baseline calcium score. We can see that baseline calcium score was picked by every single model, and in fact, it's actually evaluated as the most important feature, regardless of what category that we're looking at. It's always the most important feature for the follow-up calcium score. We can see body mass index baseline was picked many times in a clinical model feature selection. For the radiomic model feature selection, a lot more CT features were selected than the PET features. Some of the features that were selected multiple times were in bold fonts. And for the combined model feature selection, so we use both radiomic and the clinical features. As you can see, baseline calcium score is selected by every single model, and it also was the most important feature to predict the follow-up calcium score. And the radiomics features were selected a lot more often than clinical features in the combined recursive feature selection results. And the features that were selected multiple times across different models were highlighted in bold fonts. I will have more discussion into this in the later slides. So we mix and match of our feature set and our classification models. We find the best combinations. Actually, for both clinical, radiomics, and combined model, we find about top 4 models for each one of the category. We performed hyperparameter grid search for each one of the combination that gave, and then we find that the combination that gave the highest cross-validation results after the hyperparameter grid search, which is randomized search with 100 iterations. So for the clinical model, the best one was random forest with SVM. Best CV score was 0.82. Radiomics model was logistic regression with features from random forest. And the combined model was light GVN gradient boosting with features from light gradient boosting. And we can see from the internal validation, the combined model with both radiomics and clinical features had the highest cross-validation score. Now we also want to test our final model on the testing set. So we tested on both the radiomics from the manual and the air segmented contour. And interestingly, the clinical model that had the highest performance on the testing set, while the combined model had the highest performance on the internal cross-validation. Some of the discussions. Yeah, as mentioned, the combined model had the highest internal cross-validation score, while the clinical model slightly outperformed the combined model on the external validation. But because the combined model had the highest internal cross-validation, it will still be selected like in the actual application. And because of that, we believe radiomics features still have potential in giving more additional information to calcium score progression. And we also noted that radiomics features were more frequently selected than clinical features, which means radiomics feature potentially is of higher importance than the clinical features to give a prediction of calcium score progression. So baseline calcium score is the most important feature, and that is why the clinical model has such a good performance, and artery segment was the least important feature. First order features and CT features were more frequently selected, and these are some of the frequently selected CT and PET features. So, but each one of the features is a mathematical quantification of the medical images, but it also describes artery characteristics such as texture intensity, spatial resolution, and offering different insights into potential pathology. But this is something that we need to discuss, like in deep discussion with the clinicians, trying to understand what the pathology indications of each individual radiomics features are. So for future, we can use other feature engineering techniques such as hierarchical clustering, PCA, and we can also try to, other than predict follow-up calcium score, we can try to predict other clinical endpoints. This study lacks overall survival data for the patient, but it's something that we can use for using with the expanded cohort. Larger multi-center studies is needed to validate these results. Okay, conclusion. So, firstly, the first thing that we did was the feature stability analysis. We identified all the stable features. We found first order and GLCM features were the most stable, while shape features were the least stable. We found image filtering to have much higher influence on stability than bandwidth, and we also find RC and LAD have much higher stability compared with the others. Univariate analysis, we found CT features were more relevant to PET feature, were more relevant to calcium score than PET features, and with similar finding as stability, image filtering impacted the feature relevance a lot more than bandwidth. We also found the original image with 0.1 SUV to be overall optimal. Multivariate, we found radiomics features, especially CT-based features, dominated over clinical features in feature selection. Combined model had the highest internal cross-validation, but was surpassed by clinical model in the external test set, suggesting potential advantage of utilizing radiomics features, but everything needs to be further validated using a much larger and multi-center study. Future work, we need to investigate repeatability and reproducibility of the radiomics features a lot better with the test-retest studies and other reproducibility studies. As mentioned before, other feature selection techniques that can be used other than the one that we used in this study. There's other partitioning strategies for the calcium scores can be used according to Budolf's, all of the publication from Budolf. And we should also be using other clinical endpoints like overall surviving for comprehensive patient outcomes. Although it's lacking in the current clinical trial. Also in the future, we can use the deep learning method to evaluate, to go for a different approach. Sorry, I'm going a bit over time, but this is the end of my presentation. Thank you very much.
Thanks, Juliet, for that presentation. That was really excellent, and it represents a lot of research conducted in a relatively short period of time. So well done on all of that. I noticed that Mubasha has a question. If it's okay, I might jump in with my own question first, and then we'll go to Mubasha. So one of the questions that I had was perhaps slightly general regarding the radiomics field in general. So a lot of radiomics models sort of get to the stage where you're at now, right? So they're trained on a sort of one data set, and then they never proceed past that point, right? So they never actually make it to sort of bridge that gap between this research phase and actually implementing them clinically for the prediction of the desired endpoints. So my question is, what steps would you take in order to bridge that gap? So to take your model from where it is now into something that could feasibly be actually implemented in the clinic?
Firstly, I believe the clinical model needs to be stabilized. So we cannot be continuing training the model when a model is not stabilized. I think secondly, for the problem with all of these models not being able to make it to clinic is because the tiny amount of samples that we have, and the limited profiles of the patients that we have. For example, my study is only early stage diabetic patients, which means my model potentially can only be applied to early stage diabetics patients rather than the larger profiles of the other patients. So the steps that need to be taken, as mentioned many times in this presentation, is definitely a much larger cohort with a diverse patient profile, a multi-center study. And if a model can be trained using that sort of data and it can be stabilized and implemented clinically, I believe so. There is a little project Martin's been working on for decades. I think it's a containerized AI solutions within the hospital network. So it's decentralized AI solutions, so that we'll be able to train on all of the patient data without too much of the ethics approval. Because we are implementing containerized AI solution within the hospital network, and we're only outputting the parameters out, so it's not violating any of the ethics. So in this way, we kind of will be able to achieve a multi-center study and train such a stabilized model with diverse patient profile. And the next step is trying to convince the clinicians that this is a good model, and the next step is to implement it clinically.
Great, thanks, Juliet. I would just add that probably something we should also consider going forward is prospective validation. So we'd like to validate it on a prospectively acquired data set. Mubasha, did you want to jump in with your question?
Yep. Okay. Thanks a lot. Good presentation, Juliet. My question is that when you made the 3 classes of classification scores for the machine learning, what was the distribution, and was there any actually study based on which you actually classified them?
Yes. So the person I mentioned in the presentation, Budolf, he's a cardiology expert, and he's published many papers on how to partition the calcium score into different classes. I took one of his approach. He has suggested like 6, 7, 8 approaches. I just that numbers, how I partition the calcium score, is more based on one of his publication and one of his approach. And in terms of the distribution of the different classes, I have a slide that I wasn't showing because my presentation was going too long. I did investigate the distribution of different classes. sorry, I believe it's right here. It's one of my hidden slides. So this is the training set distribution of class 012 and the testing set distribution 012. So just there is an imbalance in the distribution, but we just kind of make sure that the training and testing set, the distribution of different classes is kind of stratified so that, you know, it's similar in both training and testing set. But you're right, there is an imbalance in the amount of instances, and the class with the least instances have the worst performance.
Yeah, it is expected. And also one interesting thing, if you look into it, that actually these numbers are too small for me to read. So you can actually look into it at how oftenly it is actually so you can see that actually how oftenly you can actually misjudging about the or misclassifying 0 and 2, because they are technically 2 apart and they should not be actually misclassified. So this is these are one of some of the analysis which you can look into it using these confusion matrices.
Yeah, that's
just in the
that's a very good point. It's something that we can investigate because that would be a huge misclassification.
Yeah. Okay.
Thanks,
well
Natasha.
Thanks.
Thank you very much.
Just
Natasha.
to add on to that, Juliet, so is the 2 class representing more progression in terms of the calcium score?
It's not really representing the progression, but what is the number at the follow-up calcium score? So we will predict.
Right. So it's a higher number, though, right?
It's a
okay.
higher
So
number.
which class do you think it would be more important to minimize your errors in?
So definitely it should be the high class, because that will indicate. So our precision and recall metrics should all be looking into the class 2, because we are more interested in the patients, you know, if it's correctly classified as high risk and incorrectly classified as low risk. So it will be class 2 for the precision and recall.
Great, thanks, Juliet.
Thanks, Jake.
Thank you. I think if there's not any other questions, we might just move on now because we're a bit behind time now. So thank you, Juliet, for that excellent presentation. If you don't mind stopping your share.
Yep. Sorry, guys, it went too long.